Assalamualaikum and good day everyone. So in the previous lecture we have learned about the electric flux density vector D is equivalent to epsilon naught of electric field intensity. We also learned about electric flux, and we also learned how to actually obtain the flux. Total flux is actually equivalent to integration of d dot your ds, and the electric flux is actually the same as coulomb. So let's say if you have electric flux 4, means it is 4 coulombs. Okay, now we go to the next lecture, which is the Gauss law. So far, what we have learned let's say we have a volume charge. This is a general representation because it also contains the point charge, the surface charge. Okay, so from here we can determine our electric flux intensity. We also can determine our force. So here is solution using the Coulomb's law. And from here, you also know that from E, you can determine your D, which is related by this equation. Now there is another solution that help us to determine our electric flux density. That is the Gauss law. Which we're going to cover in this lecture. Gauss law states that the total electric flux through any closed surface, okay, I pick up the point, is equal to the total charge enclosed by that surface. You can use Qn. Okay, I repeat, Gauss law states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface. Okay, Gauss law is much simpler to determine your D compared to using your Coulomb's law. Okay, but there is condition for that. Okay, Gauss law considers point charge, or infinite line charge, or infinite surface charge, or volume charge. So imagine you have a spherical imaginary boundary. Let's say you have your point charge of Q1 here, and you have another point charge Q2 here, and let's say you have another point charge here Q3, and you have another point charge outside this boundary let's say Q4. So the Gaussian Gauss law only considers the closed surface. Okay, for example, to determine the D, it is here. For example, you want to determine the electric flux density D here. So this is your Gaussian profile. The Gaussian law states that total electric flux through a closed surface is equivalent to the total charge enclosed by that surface. So here, your total charge in the enclosed surface, you have spherical here, then for example, closed surface, and you have, remember this is a scalar quantity, so D vector D and your differential surface, for example, you want to take it here, and what actually relationship with this and this that will produce scalar? Is it dot across? Yes, it is dot. So in this case, what is the total charge enclosed? For the electric flux density here. So certainly it is Q1 plus Q2 plus Q3. So why is not add with Q4? Because Q4 is outside the surface, outside the enclosed surface. Okay, so this is your equation. For the Gauss law. So this is equivalent to your total flux. Okay. So far so good? Okay. So this is just like a closed surface, okay? Your surface like shape of circular. Then it is the charge, total charge is actually the one that within that boundary, and we don't consider the one outside, okay? So here is simply Q1 plus Q2 plus Q3. Okay. From here, from your previous lectures, you also know that Q enclosed for the volume for the volume case, it is triple integral for volume, right? And what is the corresponding here is rho v. And this is your dv. For the spherical charge, what is your dv? Sorry, for your spherical coordinates, the volume is what? Is r squared sine theta d theta dr dv. Okay. So you can read through the article, okay, from page 136. Okay, there is wealth of information. Okay, now without further ado, we go directly to the practice exercise. Okay, let us see for 4.11. Okay. (4.11) state that a charge distribution in free space has rho v equals to 2r nanocoulomb per meter cube. Why meter cube? Because it's volume. Okay, for 0r less than 10. So this is your limit of your radius, and 0 otherwise. What does it mean 0 otherwise? Mean other than this limit, let's say you have R11 and so on, it is 0 for the rho v. Determine E at R equals to 2 meter and R equals to 12 meter. Okay, we extract the information first. Okay. The first information, we have rho v equals to 2r nanocoulomb per meter cube for the range of r from 0 to 10. And then it mentioned 0 otherwise means it is 0 for your r. Here is equal, right? So it must be greater than 10. Then the question wants us to find the E at r equals to 2 and E, vector E, at r equals to 12. So far so good? Okay, now we take away the book. Now we try to solve the question, okay? So the question wants us to find the E. Okay? So we start. From the previous presentation, Okay, we try to use this. Q and close equals to close integral d ds goes to triple integration rho v dv. We also know that actually d is equals to epsilon naught of vector electric field intensity. This we learned in the previous lecture. Okay. So we substitute here the integration. Then you have epsilon naught of E ds. And this one will be your triple integral rho v. And how about dv for spherical? R square sine theta dr d theta d phi. Am I correct? So that we not forget about there is element component of R inside our rho v, so we can highlight it. Okay. Now let us first consider the first condition according to the boundary. Let us consider this condition. Okay. For R from 0 to 10, so the integral of this is your 4 pi r square, right? Your surface, your Gaussian profile, then you put your here, then what is your rho v? Is 2r, nano coulomb per meter square, cube. Don't forget there is nano here. Then you put your r cube r squared sine theta dr d theta d phi. You also know that from your previous in mathematical engineering or from your schooling, the integration of sine will produce what? Can you guess? It is negative cos theta. Now we want to know the limit of our r here. Okay, so our r from this case is 0 until r. Okay, because it can be either within 0 until 10. Then what is our theta? It is a complete spherical. So your theta is from 0 until pi. You know, right, way to evaluate your pi, your theta. It is z, this is 0, then it going down until here is pi, okay, for the range of your theta. And then your phi, it is complete spherical, so it is from here until here, so it is 0 until 2 pi. So far so good? Okay, now integrate this. Okay, you have 2. You have r to the power of 3, right? So it's actually r4 over 4. Am I correct? This is 2. Then what is your limit? 0 to 10. 0 to r, sorry. And for the sine theta, you have negative cos. So you have here, you can directly calculate it. So not to waste your time, okay, it's just simple. Negative cos 180 minus negative cos 0. Okay, so you get 2. How about phi? Phi is the same. It is between 2 pi to 0, so it's just 2 pi here. So simplify the equation. This one will you cancel this out. And we'll cancel this out as well. So you will left with 2 r to the power of 4. Then so this is your ds, because this will result in scalar, right? This one, your epsilon naught, and sorry, so this is your E, your magnitude. So how you get your E? Your E is actually epsilon naught over 4 pi r squared. Remember that your volume charge density is in nano. So don't always remember there is nano at the back, okay? Then this one cancel out. You have r squared. This one cancel, you have 2. Then you have r squared over epsilon naught 2 pi. Sorry, there is pi here as well. So basically it is cancelled out as well. So you have r square of 2 epsilon naught. remember, the question is asking about vector. So our equation that we solve is containing only the magnitude. So we need to find, this is your E. So what is your vector? So your vector is in R, okay? Pairing of R. Sorry. A, okay? For example, let I rewrite it so that you'll be clear, okay? So don't forget that you have nano here, okay? Nano. So your E is R square 2 epsilon naught with AR. The unit for your electric field intensity is volt per meter. Okay, there is nano here. If the question is asking the magnitude, okay, it is R square over 2 pi epsilon naught nanovolt per meter. Okay. Now actually you have your E, the general E, in this radius. But the question is asking for E for this R equals to 2. So E R equals to 2, okay? What is the value? Okay? So you have your 2 square, you have your 2 epsilon naught you have nano, you can put 1 nano here, in unit direction radius. So try. What is your answer? 2 square times 1 nano divided by 2 times what is your epsilon naught? Okay, constant 32. Okay, so you get the answer is 225.9. okay, unit direction radius, and the unit for E is volt per meter. So this you settle for this case. The question also requires for R equals to 12. Okay. The next question is asking for electric field at R equals to 12. For this condition, we actually have two summation of integral, because it is containing the surface charge, containing inside the spherical charge, inside the Gaussian profile, and then the case where it's outside the Gaussian profile, which is R more than 10. Next, the question we're asking about the electric field intensity for E at R equals to 12. First, we need to know that there is two regions now. One is less than 10, where you have rho v having value, and for R greater than 10, where rho v is actually 0. Okay, so consider this case. Consider the same equation. But this one we have components, different components, because this one R less than 10 and we have R greater than 10. Okay, so you have triple integral here, rho v dv, plus triple integral also to make it short. Okay, rho v dv. It is mentioned that for R greater than 10, the rho v is 0. So don't waste our time on this. So this is 0. So we focus on this part. Okay. Now here, what is our range of R? 0 until, for example, they say R1. Okay, and then your theta is 0. Okay, I write like this so that you understand. 0 theta equals to pi. Then the next one is phi equals to 0 until phi equals to 2 pi. Given just now, the rho v is actually 2r nano. Okay, don't forget nano, times your r squared sine theta dr d theta d phi. Here, you know, actually your R1 is actually 10. Okay? But we substitute it later. Now we take out the constant. Okay? So here is actually 2 nano. How about here? You have R four over 4, right? And this one is your R1. How about the sign? You know, integrate from your mathematical engineering mathematics or in your school. Integrate sine theta, you will have negative cos theta. Okay. So what do you have here? Again, we can take the negative outside. Okay, cos theta, cos 180 divided by minus by cos 0, you have negative 2, then you have times by negative again, so you have 2. How about the phi? The phi is from 0 to 2 phi, so you only have 2 pi. So cancel this, and this. You end up having 2 pi R14 nano. Now, taking this one down, please take note that this R1 is not equal to this R. Okay, that's why I put it different notation, because this one is actually considering the R equals to 12, the left side. And this one is actually considering R equals to 10. And this one is, you remember there is two components just now. This one is R less than 10. This one is R greater than 10. And it's equivalent to here, which R equals to 12, which actually cover the inside quotient profile and outside quotient profile. So now we put here 2 pi R14 times 1 nano over, we bring it down, 4 pi R squared, epsilon naught. So you see, where can you actually cancel out? So you cancel this one out, you will have 2 pi. Is there anything more to cancel out? No, right? So now, so your E is actually equals to R4 over 2 R square epsilon naught times 1 nano. So this is your E. But remember, the question is asking electric field intensity which having vector. So you need to provide a vector. Okay, this is the unit for electric field intensity, which is volt per meter. Now, the question is asking E R equals to 12. So you substitute, knowing R1 is 10, then 1 nano, okay, over 2 times your epsilon naught. Then R square So you try to solve this further to get the answer, okay? Thank you.